Task Manager is actually terrible at telling you if you have something running on your computer that's dangerous. A lot of the work is left to you to figure that out. But how do you do that exactly? Well, here are 3 levels of evasion techniques that malware uses to keep itself hidden from you and potentially your antivirus. And I'm going to show you how to spot each of those 3 techniques. By the end of this video, you will know the ins and outs of every angle involved, from the hacker's methods of attack to your ways to diagnose the processes in question and see what's going on your machine. But before we get started, given that you are in part learning how malware is written, this video is for educational purposes only. I am not incentivizing any illegal activity. I'm not participating in any illegal activity. Please be responsible and know your local laws. Let's get started. All right, so the first method is name spoofing. Name spoofing is very easy to grasp. All it involves is changing a malicious executable's name and icon to look like a legitimate one. Here's an example. On the left is a tool that lets me zoom and pan around. It's really useful. I really should use it for my YouTube videos. And the one on the right is not that. Instead, it acts as our payload. Now, this is just a message box, but an attacker would replace this with an actual malicious payload that establishes persistence so it can survive a reboot and do all kinds of crazy stuff like mining crypto and stuff like that. How did this work? How did I change the second EXE's icon so it looks exactly like this one? Well, it's pretty easy. All you need is a tool like, not Resource Monitor, Resource Hacker. And all an attacker would have to do is drag their legitimate program that they want to take the icon from into Resource Hacker and then take a look at the resources, probably the icon. Let's take a look. We have what looks like a bunch of different icons in different sizes. We don't need to go too crazy with this. 256 by 256, probably 64 by 64 would be good. So if we want to save that, we can just right click this entry here, save as a .ico. And we're going to call this legit icon. It doesn't really matter what you name it. Let's go ahead and remove this, and I'm going to go ahead and replicate it in this virus right here. So we're going to go ahead and open up Resource Hacker again. We're going to drag our virus.exe, and you can see there's no icon folder. Well, how do we add one? Probably this thing that looks like a picture. Let's add that. We're going to select the ICO file right here, legit icon, and you'll see the resource type changed to icon group. We're going to leave that as is. And now we can see that if we hit save as, we can replace this virus.exe with something like viruspatched.exe. So we can open it up and it executes the payload and the icon is the same, but you'll notice if we change this to zoom it 64, it's not going to work. There's already something here. How do people get around that if it's in the same folder? Well, I actually used a trick. I replaced the O's in zoom it with a character that looks exactly like it. So it's technically not named the exact same thing. All you have to do now is just paste in the O's right here, and it looks completely identical if it weren't for this file size and other stuff like that. So if you wanted to take a look at this in Task Manager, you would just need to go to the Details tab and take a look at Zoom It. You can see there's one right here. This is the one that lets me zoom in. It's pretty cool. And if we run this one right here, we can see another one pop up. But a little side effect of using fancy characters, if we continue searching for it, since we type the not special character, it's not going to show up. And there's a little bit of an added benefit for the attacker of being a little bit more difficult to go ahead and find the process and kill it. But this method isn't likely to work anywhere your antivirus would catch this immediately. All right, the next method is process injection. And this is where it starts to get a little interesting. We are injecting our malicious process into a legitimate one. So it's a bit harder to kill it. And we do this through a DLL. Now, a DLL is very similar to an EXE. The only difference in this case is that we need an EXE to help run the functions and the logic inside a DLL. In other words, a DLL can't run on its own. So we're going to attach that DLL to our legitimate process. And that legitimate process can be anything. For instance, explorer.exe. It handles the taskbar and a bunch of other stuff. You can see that if we restart it, everything gets nuked. This is what an attacker would do. They would get their injector. This, if it were malware, would be run on your machine, the victim machine, and it would do all this automatically. But I made a little tool here that would make this easier for me since I'm recording them. All I need is the process ID of Explorer 2712 and a path to the malicious DLL. Right click, copy as path, paste, right click, and you can see the DLL is injected into explorer.exe. Now, we can't see this in Task Manager. All we see is a legitimate process. If we open the file location, we're going to get our legitimate file back. This isn't going to tell us much of anything. So how do we actually see the DLL being loaded? Well, this is why Task Manager kind of sucks, and we need something a bit heavier. So I have Process Hacker here, and Process Hacker is basically Task Manager on steroids, and we wouldn't know where this process process is, we can see that we can't see our DLL. This is just the injector that we ran with it. That's not going to tell us very much. So how do we actually see what's being loaded? Well, we're going to have to look at the modules tab after clicking properties, and we're going to have to do some digging. So we know this is dummy payload.dll. That's where it's loaded right here. And if we wanted to, we can unload this. Okay, so Explore exe must have restarted because it looks like 2712 isn't its process ID anymore. Yeah, 804. Yeah, that crashed Explore exe for some reason. That's kind of funny, but there you go. So now that you see the effects of it, let's see how it actually works. At a high level, this is what would happen. This is what they would need to do. First, something would run the injector. Let's say they have a Trojanized program somewhere. That Trojanized program's shellcode would probably download something off the internet and then execute it. And what it executes is the injector. The DLL injector would then find the DLL on disk dropped by the initial payload, and then it would get its victim process to make a load library call and load that DLL into its memory. Now here is what that would look like. And keep in mind, this is a demo program. This is not meant to run on a machine. Don't use this for anything malicious. This is just for educational purposes only. So as you can see, first, it's going to ask us for a process ID. Once we get that ID, it's going to take a snapshot of all the running processes at that time. If it doesn't work, break out of it. Going to get the size of all the processes. That doesn't work, break out of it. And then it's going to go through each process looking for the process ID that we're looking for. And if it doesn't find it, break out of it. So let's give it our process ID. Let's give it a random one this time. Let's do Microsoft 365 Copilot 7360. 7360. All right, it found it. Now it's asking for the DLL path. Let's go ahead and paste that in again. As you can see, Microsoft Copilot popped up with a window. That window is our DLL again. So what happened in the meantime? If we read this, we can see that one validated the DLL file existed, got its absolute path, which we already provided, opened the target process, gave us a handle that we can reference it with, allocated the memory in the target process, which was 48 bytes plus an extra byte for a string terminator, then goes ahead and writes to the memory, finds the load library A address in the kernel 32 DLL, which is not part of our target process. We're going to create a thread in the target process, and then we're going to get it to call kernel 32's load library A to load the DLL. And if all that works, we should get that. So what does that look like? Well, we use a get file attributes call for the DLL path that we specified earlier in the program. If it doesn't work, break out of it. For resolving the DLL, we're going to make an array absolute path and set it to the max path constant, 260 characters. And if that doesn't work, break out of it. If it does, it'll print it to the terminal. It'll then open the target process based on its process ID from earlier using an open process function with all access based on its PID, and then put all of that info in our hprocess variable so we can use that to make more changes. If that doesn't work, break out of it. If it does, print it out to the terminal. Now we're going to use the mother of all calls, virtual alloc ex extended, and we're going to allocate memory. We're going to specifically allocate the path length amount of memory in our process that we established up here at open process, and we're going to set its permissions to just read and write and not execute, since we're just writing a string. That string being our DLL path. If it doesn't work, break out of it. If it does, print it to the terminal. So now we've allocated the memory to our correct process, and now we just need to write the path of the malicious DLL that we're loading and then convince it to run that code. So first we're going to write the memory to our process. This is the memory we are writing. This is the amount of it we are writing, and this is a variable it sets that will return the amount that was written. If it doesn't work, close everything out and clean everything up. If it does, print it to the terminal. And now it gets a little fuzzy because load library A isn't in our malicious DLL. We're going to go ahead and call this from kernel 32. And in case you didn't know this, most programs, in fact, I think all programs call on kernel 32 because most programs are wrappers for these low-level APIs. And if we go to properties and modules again, we can see that there are a lot of APIs. We can find kernel 32 in here somewhere. Kernel base, kernel 32. Almost everything that a program would ever need to do actually just calls these low-level functions, and then they do all the heavy lifting and then return the results back. But the thing is, since all of these functions are calling the same kernel 32 DLL, it's going to be in the same memory address every time, since there's only one kernel 32 DLL being loaded. So we can take advantage of this because we can figure out where this thing is and then tell our process to call it from that DLL. That's what this function does, not this one. Now that we found everything we needed, we can make a new thread, a new lane, so to speak, for operations to be done under one process. That process being our victim process. We're going to have it call this function at this address, and then we're going to pass our DLL path as a parameter. If it doesn't work, break out of it. If it does, it's going to wait for everything to finish. It's going to set the exit code to 0, and this is going to set it to literally anything else if it works. So we know if the exit code is not 0, that it worked. It's going to close everything out and make everything nice. It's going to close the handle, free the memory, because now the DLL is loaded and is executing code. And this is our main function that just prints everything out to the text, gets your input, and then calls this big function that encapsulates all of this stuff. Anyway, this will be in GitHub in the description if you want to take a look at it. This is not what somebody would probably use just because, one, there's a lot of debug information in here and it's very transparent. Something like this would definitely be very heavily obfuscated, and finding the DLL on disk and would probably have some dummy functions in here to throw off behavioral-based analysis and antiviruses and stuff like that. So yeah, now you know this from every angle, the defensive side, high-level side, and what it would look like from an attacker writing this. So now for technique 3, process hollowing. Process hollowing is even easier to get than process injection. You are starting a program frozen, so it doesn't execute any instructions. You are then wiping everything out of that instruction set, its memory, and then you're going to replace everything with malicious code. Hard part comes in because Windows normally handles all of the loading itself. So there's a lot of low-level stuff you have to do to make sure everything works out. Here's an example. This is a dummy payload. All it does is execute a message box, but when we run this, it's going to make something else execute this code. So you can see right here, it looks like we just ran this, but it's actually running from Notepad, which doesn't make any sense. And if we go to the task manager, if we look up Notepad and we find where it is on disk, if we open the file location and open it, it's Notepad. It looks like we have 2 instances of the same program. So now you would think, all right, let's go ahead and see if it has any DLLs loaded, right? So that's what you do. You open up Process Hacker and you look for notepad.exe, and to get its properties, go to modules again, and let's look for our payload.exe. It's not there. In fact, all of these DLLs are legitimate. So if this is running on your machine, how do you know what to look for? Well, the only real way you're going to see for sure is to look at its memory directly. So let's take a look. Our biggest sign right here is this read, write, and execute section. Now, sometimes this will be read and write, so it won't be very easy to spot. But in this case, this is almost never going to be the case. You're never going to find a read, write, and execute section because that means the code can modify itself, which is pretty much only used in a malicious context, or if people or companies don't want their code being reverse engineered, like with anti-cheats. But an anti-cheat shouldn't be running in notepad.exe. And if we take a look at the memory by just double clicking, we can see right here, payload executed, process hollowing successful. We had to go down to the memory level to see this. And this is where things with your antivirus start to get a little bit spotty. It may not see this, but most of the time it will. All right, so what needs to happen for an attacker to be able to pull this off? Well, this is what happens behind the scenes. First things first, this step is the same. Something runs the hollower. That's usually the shell code that runs from the Trojanized program. Same thing as before. Next step is kind of the same. The hollower finds the payload exe on disk, except this time it doesn't actually need to be stored as a file at all. It can be stored in the registry. It can be encrypted, encoded, everything. All the operations can be done inside the hollower this time because we're not using the load library function. We are doing everything manually. So we don't have to rely on a high-level function from the Windows API to take care of that. It'll convert that file into memory format. This usually means taking the sections because executables have sections that contain code, icons, read-only data, read and write data, and it aligns it to what are called memory blocks, which are usually 4 kilobytes in size. And the reason for that is because each block can only have one set of permissions active at a time, whereas on disk, it doesn't really matter, and it's put that way on disk to save space. So that's what this is really doing. The next thing the hollower does is it finds the victim process on disk and then runs it frozen, specifically called suspended. So it's not executing any instruction. It will then unmap all of its instructions using a call to ntdll, which is actually underneath the Windows API. After everything's zeroed out, we're going to go ahead and map our payload exe into the victim's process memory after adding additional memory. And then we're going to be doing a lot of manual stuff after that, like fixing the hard-coded addresses and the imports to other DLLs, because every program uses DLLs. If Windows doesn't handle that, we have to. And after all that's said and done, we resume the program, and that's how we get our program to look like it's running from Notepad. So I have a hollower.c that I'm going to put on GitHub as well. This is quite a bit more complicated, and I'm not going to go through it in so much detail, but I will go over a few more things. It's going to look for specific bytes to verify that it is the right file, map it to memory, create the target process in a suspended state, and this is an important one. Get the thread context and read the PEB. What are those things? Well, we want the thread context because we want the values stored in the registers of the CPU. And registers are basically little blocks of memory that the CPU uses for doing operations. And certain registers have certain values. For instance, where a program is in memory, where the current instruction is, the first instruction that gets run in memory, which is not the same thing as the first thing in memory under that program. And the thing that has all this information is the PEB, which we need to find because we don't know where the program is loaded in memory. But we know where the PEB is because it's in one of the registers in the CPU, specifically the RDX register in 64-bit programs. So this will read the RDX register, jump to it, jump a few bytes forward so we can see the beginning, in other words, the base address, go there, and now we know where to start mapping from, since we need to find the beginning of the program. It'll then go ahead and make this call NT unmap view of section. Any function that starts with NT or ZW is underneath the Windows API. It'll go ahead and allocate the memory using the virtual alloc EX function. And now we're in the patching stuff up phase. Step 7 is something we have to worry about if our code jumps to direct addresses in memory. In other words, doesn't jump forward or backward a certain number of bytes, but instead goes to a very specific address. This is important because if our program loads in a spot that it's not expecting, the addresses are going to be wrong. So we need to adjust them by the difference in where the program is loaded versus what it expected, and then add that same change to all of the hard-coded addresses so everything works out. Sometimes you don't need this because programs can be position independent. Next, we have resolving the imports. This is pretty complicated. I'm not going to explain it in a video, but all you got to know is that the DLLs have to be referenced properly so the functions can be called. Anyway, now that we've made all of that, we can go and allocate what we've been working on to our target process in its memory. We'll go ahead and change the PEB to add the base address and the entry point, and then we are going to run it. That'll start it at the entry point. It'll close everything out and make everything cleaned up. And now you have malware disguised as Notepad. And that's it. Now you know everything. Now you know how to disguise files, inject into processes, and disguise your processes so much that you have to actually look at the memory to be able to tell that it's not the program you're looking at. Yeah, hope you guys enjoyed. Stuff's in GitHub in the description. Go ahead and check it out. Subscribe if you like malware.